What is it like to bear witness to a Nobel Prize-worthy discovery in the making? Today on our show, we have a very special guest, Adam Riess, who will share just that kind of story. So stick around. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper.
Adam Riess is an astronomer and a professor at Johns Hopkins University. Among other things, he's probably most well known for his work on using supernovae to measure the expansion rate and expansion history of our universe. Adam's won all kinds of awards, most notably the 2011 Nobel Prize in Physics, which he was awarded along with Saul Perlmutter and Brian Schmidt. This prize was given for their observations which showed that our universe is not merely expanding, but that it's expanding at an accelerating rate. The fact that the expansion rate of our universe is accelerating requires that space contains a great deal of energy beyond that found in matter or other kinds of particles. This stuff we call dark energy. We don't really understand it, but Adam and others' work shows us that it's a big, important part of our universe. And today on Why This Universe, we have Adam Riess here with us to talk about this momentous discovery. Welcome, Adam, to Why This Universe.
Oh, thank you very much for inviting me.
Oh, it's great to have you on. I think you're our first Nobel laureate. Is that right, Shalma?
To my knowledge, yeah.
Hopefully not our last, but it's a good place to start.
We'll see how well this goes and if you get any more.
Yeah. All right, so we're kind of doing a retrospective here. We're going to talk about how you and your colleagues discovered the universe, the expansion rate is accelerating, and what that tells us about our universe. So let's go to a time before these measurements were made, like maybe to the early 1990s or something, and kind of paint a picture of the state of cosmology around that time and maybe your place in it as well.
Sure. So I would say in the early 1990s, there was a growing tension between observations of the universe and the theoretical perspective of what should be. And the tension centered around the value of the mass density of the universe, what we call omega matter.
This mass density tells you, on average, how much matter there is in a given volume of space.
And so observers were looking out, counting galaxies and clusters of galaxies and things like that, and trying to basically do a census of how much matter was out there.
And to describe this density of matter in the universe, physicists normally do it in terms of the so-called critical density. So the critical density is a specific value for the matter density, the density of matter in the universe, that would lead to a universe that is eternal and unchanging, one that isn't expanding or contracting.
If you have more than the critical density, then the universe will eventually stop expanding and contract. If you have less, it will grow without limit. And if you have exactly the critical amount, it will kind of plateau and towards a constant size.
A useful analogy, I think, is to think of a rocket being launched with, it could be escape velocity. In this case, imagine that rocket is leaving the surface of the Earth, or maybe will. You could turn that around into, well, it depends what the mass of the Earth is, and whether that rocket will be pulled back to Earth, which would be like having more than the critical amount of mass, or it could be a lightweight Earth, in which case the rocket would escape. And so the question that astronomers and cosmologists had was, is there enough matter and its attractive gravity to pull that rocket back down or not? And up until the 1990s, astronomers were only finding very little matter and implying that the universe would expand forever.
So what was the tension in that? So far it just seems like there's not that much matter.
That's right. But there was a very strong theoretical perspective that the best sort of deep theories about the universe, a theory called inflation, explained how the universe would have started, what its conditions would have been like to be the way it is today. And in that perspective, omega matter would have to be right at that knife edge.
We should have the critical density of matter.
They were only finding about 30%, 20 to 30% of the, quote, needed amount. And so theorists were saying, gosh, there just must be more out there. You must be missing it.
Right.
And as people thought about how that could be, they realized, okay, well, maybe you're just counting stuff, galaxies and whatnot nearby, but maybe there's more stuff further out, or maybe there's stuff in between stuff that we're just not seeing. And so if you could actually measure the way the expansion rate of the universe is changing over time, you would essentially weigh the universe and figure out where that missing stuff was.
At the time, how confident was the theory community that something like inflation and therefore omega matter equals the critical density being, a firm prediction? How confident were they in that prediction back then?
What I remember, and now, of course, at the time, I'm, just starting graduate school, so I was not hanging out with the graybeards and the high priestess of the field, but what I understood was the most elegant versions of inflation were pretty strong. However, there were some theorists who, were getting a little antsy about seeing the low mass density, and they were starting to come up with alternatives, things called open inflation and things like that, which were efforts to sort of save the theory, even if the data wasn't matching the elegant version.
All right, so continuing down the story, we have this tension building in the early 90s. What did you and your team set out to do to shed some light on it?
So I would say in parallel, astronomers, my colleagues, were recognizing that there was a class of supernovae called type 1a supernovae, and that these provide the best standard candles, objects whose luminosity were so regular that you could use their brightness to determine their distance.
You want something that's really, really bright and that you know how intrinsically luminous it is to measure how fast the universe is expanding between us and some very distant point. And you guys started using these type 1a supernovae.
Astronomers had been more or less understanding the phenomenon of a supernova for a century, but really what they were seeing was two different mechanisms which get a star there. One, a very massive star collapsing, which can happen, at a range of masses and luminosities. And then this other very special mechanism of surpassing the Chandrasekhar limit for a white dwarf type star.
You've got a white dwarf star, like a big compact, heavy star. It's swallowing matter from some nearby star until it meets this threshold, the Chandrasekhar mass threshold, and it explodes.
And by the late 80s and early 90s, astronomers were recognizing the signature of the latter, a particular kind of spectrum, and that these ones were far more uniform than the others.
So if you want to use something like a supernova to measure the expansion rate of the universe, there's two important ingredients. For one, we need the standard candle, meaning that we need something where we know how intrinsically bright it is. Like we know if you were standing right next to it, how much light it would be emitting. And that helps you figure out how far away from that object you are. And you need to know how fast this object is moving towards you or away from you. And with those two pieces, you get this map of objects, how far away they are from you, and how fast they're moving away from you. So we got one piece down. We have how bright these objects are, these type 1a supernova. So how do we figure out how fast they're moving away from us?
When we look at the light of a supernova, it emits light at certain known wavelengths that correspond to the atomic elements we're familiar with in the periodic table. So in the laboratory, you could determine silicon and sulfur, these wavelengths of light that they emit. And then because of the expansion of space, the supernovae are being carried along by expanding space. And so the light we receive becomes, its wavelengths are elongated, a phenomenon called the redshift. And so it's the redshift which is really the thing caused by the expansion of space. So we're looking at redshifts, and then by looking at the distances, that's essentially telling us how far back in time we're looking, because distance and time are directly related by the speed of light. And so basically, it's giving us slices in the history of the universe showing us, okay, this much expansion had occurred up to this time, this much expansion to that time, greater and greater red shifts as we look further and further back in time.
Okay, so it's not just the brightness, but something about the composition of these supernova explosions that let us know exactly what the wavelength would have been if we were right next to it.
It's the shifting of the color of light. You're familiar with this in a different phenomenon called the Doppler shift. If you've heard an ambulance driving towards you or away from you, you hear a change in the pitch of the sound coming from the ambulance. When it's coming towards you, that's a blue shifting, and when it is pulling away from you, that's a red shifting, and your ear hears that change in pitch. In our case, the supernovae are only moving away, and instead of its sound being elongated, it's actually the wavelength of light being elongated, so that instead of hearing a deeper sound as the supernova moves away, we're seeing a redder color of the light.
Supernovas are really fast. First of all, how many even are there that are happening often enough for us to catch them? And then how are we catching them in the moment?
Right, that's a great question. So the moment of explosion occurs at some instant, but then it takes several weeks for the supernova to grow to its brightest point. And then it falls. It's kind of, at that point, like a bonfire, if you will. The spark happens, but then it reaches a very bright point, and then it fades away as all the fuel is sort of used up. So a supernova will occur in a galaxy like ours, maybe once a century. If we just stare at some distant galaxy waiting, you'd have to be incredibly lucky. It's just not going to happen. But because there are so many galaxies in space, if you could take a big enough image that where the image itself contains tens or hundreds of thousands of galaxies, and then you take another picture of that same spot in the sky, maybe 30 days later, in that intervening time, one of those galaxies, you don't know which one, but one of them will surely have had a supernova go off. And so if you can digitally subtract one image from another, all the galaxies which haven't changed over 30 days will just disappear, but you will see that new point of light on top of some galaxy. And so that's how we find one is, we don't pick our galaxy, we search a lot of area. It's the analogy I like to say is it's like winning the lottery, but if you need to win the lottery, you just buy all the lottery tickets, and you don't know which one will hit, but you're going to win. And so it started to become clear by the early 1990s that there was a sort of revolution afoot of our ability to measure distances and redshifts, which are the key observable quantities to measure the expansion rate of the universe. And also, if you could see them far enough away, to measure the past expansion rate so that you could actually see how the expansion of the universe was changing as a consequence of how much matter was presumably slowing down the expansion. And so at that point, there were two groups, more or less, who were planning to do this. The first group to get started was at the Lawrence Berkeley National Laboratory and ultimately led by Saul Perlmutter. And they came from more of a physics background, a particle physics background. So they were sort of maybe less following the development of the Type 1a supernovae, but they were quicker to search for the distant ones to compare to the nearby ones. And by the early 1990s, we're trying to get an answer to this question. Our group, the High Z supernova team, nucleated around a few groups that were studying the Type 1a supernovae themselves, learning how to standardize them, and then thinking as an application of that, we could search for distant ones and try to measure this change in expansion rate. And so Brian Schmidt and Nick Sensef, Bob Kirshner, and then later, Alex Filipenko. This is the team that I was originally on as well, and others from the Kalan-Tololo survey that we began to also search for distant supernovae. And so by the early 1990s, mid 1990s, the race was on to get an answer to this question.
So now we're at this point, Adam, where we've got two competing groups, the Supernova Cosmology Project at Berkeley, and then your High Z supernova search team. How did that race go?
It's interesting to consider, why are you competing? What does that even mean? Is this like a foot race or something, and why is there a need for that? And because we want to use the world's most limited resources in terms of astronomy measurements, like the Hubble Space Telescope in the early 90s. There was only one of them. It was brand new. There isn't enough time to do everything astronomers want to do. So every year you're putting in proposals, and at some point you are competing, saying, well, we want to do this kind of experiment, and another group saying, well, we want to do it. And so that's the part that ends up being a competition for resources. And yet, through the wisdom of the director of the Space Telescope Science Institute, which runs Hubble, Bob Williams at the time, he recognized this was such an important experiment that it was crucial for two teams to do it and to be able to compare the results. And so Bob Williams actually gave time to both groups. And so the way we would make these measurements was tricky, and it was a very many steps along the way, which was unusual for astronomy. This was the beginning of what we call time domain astronomy. And so one of our teams or groups within our team would make observations of a wide area of the sky with a ground-based telescope, usually. That had a wide field of view, and this was a new technology at the time, wide field digital detectors on ground-based telescopes. And then they would reobserve that same spot in the sky a month later, subtract the images. And again, that was new software, new algorithms in the early 90s to subtract images to match the conditions of images. And then look for new points of light because one of those galaxies would have had a supernova. And then provide that information to another part of the team that was in another telescope somewhere to take a spectrum of that point of light and then identify if it was a type 1a supernova. These are very faint objects. That was probably the most difficult measurement to make, and determine what their redshift was. And then if all looked good, it looked like a type 1a supernova at a high redshift, then we would send the coordinates to the Hubble Space Telescope to maybe make follow-up observations, or we'd follow it up from the ground and go on and try to then measure the light curve and the distance and combine those pieces of information to see how the expansion rate of the universe was changing.
And how many of these type 1a supernovae were you seeing at the time?
Yeah, so it was, very variable depending on the weather and conditions. We might either get completely weathered out and find nothing, or we might find, as many as half a dozen good candidates. And that was sort of what state of the art was at the time.
Okay, so I'm thinking back to that textbook I was using as undergrad that said either the universe is going to contract one day, or it's going to expand without limit, or it's going to kind of plateau. Obviously, there was a lot riding on who was going to be able to answer that question first. Who got there first? Which of the two groups?
The Supernova Cosmology Project was ahead of us by a couple of years. They'd started earlier, and by 1996, 1997, they had collected their first 7 or so. And I recall their initial answer from them was actually high omega matter, meaning that the universe was decelerating a lot, but they had fairly large uncertainties on that measurement. And so, that was going to be still far from the final answer. Our team began in 1995, found our first high redshift supernova then, and by 1997 had collected about 4 or 5. And so by 1998, we put out our first conclusions from just 4 supernovae, in which we found that the universe was not decelerating a lot. And the other team had found a very distant type 1a supernova, which gave them even more leverage. I think it was redshift 0.8 at the time.
That's a long way away, yeah, for context, yeah.
It is. And that object, plus some further analysis of the data they were up to 8, also indicated that omega matter would be not a big number. And so that was the state up until late 1997, I would say. And so I'll just say from my perspective, I was picked to sort of lead the analysis of the first big sample, and big at the time was maybe 15, 16 type 1a supernovae. And so I was down the hill from Lawrence Berkeley Lab. I was at UC Berkeley at the time. So I was working on that data and did the analysis, did the fits, wrote a simple computer program to tell me what the mass density of the universe was implied by the data. And the answer I got from running my fit was negative omega matter, which of course doesn't make any sense.
Right. Negative matter is not a thing.
Right. So it's not a thing, but in the way we were looking at this, and what I hadn't yet noticed was that the expansion is not just slowing down, it's actually speeding up. And so, computers don't know physics. And so I had given the computer, a very simple equation to fit, not knowing yet that I didn't have all the right physics in there because I thought matter is the only thing that mattered. And so, therefore, once I could see that the universe was actually accelerating, then you need something besides matter to explain that. Matter only has attractive gravity and will only slow the expansion. If you see it speeding up, something else is going on. It's like driving a car. If you watched a car traveling, you saw it slow down, you'd go, oh, yeah, that's what the brake pedal does. Okay. And so that's fine. But if you then saw the car speed up, you'd go, well, that's not the brake pedal. That's not even the inverse of the brake pedal. That's a different phenomenon. That's the gas pedal. In our case, I remembered hearing and understanding about the cosmological constant, the energy of empty space, and how it could have repulsive gravity. It's just it had been dismissed for so many decades. It wasn't until the data was indicating acceleration that at least I realized, okay, that has to be added to the equations now. We have to allow that there's matter in the universe, yes, but there can also be some of this cosmological constant, or what we call dark energy. And in fact, the balance was shifted so that there was more of that stuff than of matter. Otherwise, the universe wouldn't accelerate. And so the initial analysis of it gave that answer. But at the time, I just thought this was wrong, that probably I'd made a mistake in the data analysis. So I began cross checking things. And so by the end of 1997, I'd run through all the analyses I could think of, and I kept getting the same answer. So I began sharing pieces of the analysis with members of my group, particularly Brian Schmidt, saying, can you check me on this? Can you check me on that? And I remember all the steps checked until we got to the last one. So you have this pile of distances and redshifts. What answer do you get for the fit? And Brian at the time was in Australia. I was in California. So there was about, an overnight delay. Anytime I sent him something, I wouldn't get an answer until the next day. So I remember going to bed very nervous, sending him, the final calculation to do, and waking up in the morning to an email from him saying just one line, well, hello, Lambda. And lambda is the variable we give to describe the cosmological constant. So he had seen and confirmed the same thing I was seeing. And that was already early in January 1998, and then began discussing it with the rest of the team. And everybody was amazed, shocked, worried, surprised, excited, all the emotions of something that, you either have a major discovery or, major blunder on your hands. By early in 1998, our group began talking about this. And much to our surprise, the other group also began talking about getting the same answer. They had at that point a much bigger sample of supernovae, and their answer had moved to the point where, with more supernovae, that they were seeing this as well. So here we were competing with this other group, and suddenly we're both singing the same song. And, that was tremendously exciting. And I think that's when the story really broke to the rest of the community that, both groups were seeing an accelerating expansion, implying that the universe is filled with this cosmological constant or dark energy.
So with this momentous discovery, physicists suddenly had to come to terms with the fact that our universe is filled with this extra mysterious dark energy. And this came along with both some new understanding, making sense of things that didn't make sense before, and also a lot of new questions.
What I did not appreciate at the time, because I was just a young postdoc, was how well this cosmological constant would fit many puzzles that were going on. So we had discussed earlier that there was the best theory of the universe's start, called inflation, said that the sum of all matter energy should be equal to this critical amount. At the time, I thought, and many thought, that meant just the matter, but this dark energy could also fill in the missing part. And in fact, it was filling in just the right amount. Another problem was it appeared that the ages of the oldest objects in the universe, globular clusters and old stars, appeared to be older than the age of the universe when we inferred the age of the universe from how fast it was expanding and imagining how long ago everything would have been back on top of everything else. Well, if the expansion of the universe is now accelerating, that means that the current speed of expansion is faster than it was in the past, and it causes you to underestimate the age of the universe. And so this solves the age crisis. So there were a couple of great benefits from this that fit the puzzle. I would say the biggest negative, of course, was that particle physicists could not understand and still do not understand how this, if it is a vacuum energy, why it has the value that it has. It, is famously off by something like 120 orders of magnitude from what you would naively calculate. And so this remains to this day a severe problem, shortcoming, I would say, of the story of dark energy.
So back in the late 80s, Steven Weinberg had this paper that at least now is famous. I don't know to what extent it was famous at the time, but he based on a argument based on an ensemble of universes, a multiverse, predicted that the cosmological constant, the amount of dark energy, should be about roughly the size that you would end up measuring it to be. At the time, were people in your community, thinking about this? Were they even aware about Weinberg's argument? Did they care about it? Did it carry weight?
Right. So Weinberg's argument, brought in an additional piece of information, what we call anthropic, which is to say, well, we're here. So, if the dark energy density was what particle physicists thought, 120 orders of magnitude greater, then the universe would accelerate apart before anything got to form. We wouldn't be here. So Weinberg imagined, okay, so maybe that would be the typical or natural value, but maybe there's a range of values that nature takes on. And, if it doesn't take on a sufficiently small value, then we're not here. So what is the largest value that would still work that to form and allow the complex structures we see to exist and ultimately for us to exist? And he derived a value that's not far off from what we have now. So this just says, well, we're here, aren't we? But at the time, I would say, and still to this day, there's always been a pretty strong dichotomy between the theoretical perspective of the universe and the observed perspective. So the theorists are, they're, you know, in a position where they are imagining all kinds of possibilities for the universe, and most of those they know are wrong, and that's okay. There's this old joke you probably heard too that to be a successful theorist, you just need to be right like 5% of the time.
Oh, that'd be great. 5% would be a really good percentage.
Right, maybe 1%. But to be a successful observer, you better not be wrong, 5% of the time.
Yeah.
And so, so we head off in these different directions with theorists imagining all kinds of things, and observers, the ones who, quote, check them or check the idea space. And so I think to the observers, it benefits us to not pay too close attention to these theoretical ideas.
Sure.
Because, on the one hand, you don't want to be biased. You don't want to fall in love with these ideas. You're more like the umpire for the baseball game. You want to call balls and strikes. And not care who wins or loses the game, where the winners and losers are the theories themselves.
Yeah, not to be biased by the theoretical expectations about how nature should be, but rather to, neutral, and as a neutral observer, find out how nature is.
Right, and I would say, in a way, the tension I described earlier was one between theory and observation, where theorists said, it'd be really easiest to understand things if omega matter was one. And so as an observer, you didn't want to be biased by that, because maybe it isn't. And in fact, what we found was it really wasn't. And so, theoretical ideas are great. In particular, we want theoretical explanation once we, see how the universe is. But, you don't want the tail wagging the dog in this case. And so it's important to keep observation separate.
So I want to focus for a minute on this period of time, like before the data's gone public. You and Brian and others are looking at this conclusion you're reaching. Was it easy to convince your collaborators that this is the right answer and you needed to publish it? Or was this contentious internally? Were people nervous? I tell you, I would have been very nervous to make such a big, bold claim, even if I couldn't find an error anywhere, I just, how do you have enough confidence in yourself and your team to put out something so contrary to expectations?
Right. It's a great question. And as I've gotten older, I've looked back at that moment with different perspective all the time. I think that, for me and maybe even for Brian at some level too, we had the advantage of youth and inexperience on our side. I think we didn't know quite what a big deal it was. We hadn't lived without the cosmological constant so long. We had just learned cosmology only a few years earlier. When you're young, you think, oh, all kinds of differences and possibilities are possible. When you get older in science, you've seen many things come and go. You've seen people make claims that turn out to be wrong. You become, I don't want to say cynical, but your bar gets higher and higher, maybe unreasonably so. And so, you go in with a perspective of, well, I don't know, I've seen things come and go. And so what happened was we began discussing this over email in a rapid chain over just a few days, where different perspectives came in, from like, hey, let's go for it, this is exciting, we're seeing something, to like, hey, let's not be wrong, that would be terrible. Remember, and every physicist carries around there, remember these 5 examples of times when we thought something and that was wrong. Of course, there are counterexamples as well, of course. And I think where we settled out, and this is maybe important to think about, is if you try to reach a place where you're right, you'll never get there, because you can't know you're right, because this is hard stuff and there's always possibilities. If you lean to a place where everything new is wrong, you also don't want to work from that standpoint as well, because by definition, you'll never be willing to kind of make a discovery. And so instead, you have to get to this place where you feel like you've done a credible job of the experiment. You've done, sort of the best that can be done. Maybe it's state of the art, but that at the end, you're reporting the observations as you see them. And, in astronomy and cosmology, we often use this word apparent. And, it has a deeper meaning than just like the obvious, like, oh, apparently so. What we really mean is, this is the way it looks on the sky. This is what we see on the sky. So, if the supernovae are fooling us, if there's some mysterious gray dust in the universe, if there's some other variable that we don't know about, then we'll all be wrong ultimately. But there's no shame in that. In fact, the right science is to report the
Yeah.
apparent observation as you see it, and allow the community together to move forward by understanding, how do we make sense of this observation, and trying to understand the physical universe. It's almost like at that point, we are proxies for everybody else. If you did this experiment, this is what you would see. And now we can all start on the same plane and think about what it means. Everybody doesn't have the time and energy to go do every experiment themselves. But if you carefully describe what you've done, and you've done a solid job, you haven't made, some blunder or something, then you can report that, and hopefully, hold your head up high, whatever happens, and say, well, there's famous experiments which have been done, that at the time we're not sure are right. The Michelson-Morley experiment's a great example. Where you say, well, I'm looking for the ether, and this is what I'm seeing. And so I think that's the place I was able to come to. For myself, I know, where I was able to say, okay, I mean, I think this is the results. This is the way it looks on the sky. Everybody needs to know this. Here's the paper.
So at the end of 1998, when your group, as well as the Supernova Cosmology Project, had both put out their papers showing that omega matter, the amount of matter in the universe, is way less than the critical density, and the difference seems to be made up by dark energy, cosmological constant, whatever you want to call it, what was the initial response from the scientific community? Now, by the time I was starting grad school, there was a consensus forming that this was real and whatever, but that was just a couple of years later. What was the first year or two after that looking like?
You could get a lot of opinions at the end of 1998. What I remember, it was about half and half, maybe 2/3, 1/3, but it was something like that. Meaning, in a crowd of cosmologists, you could find many who'd go, I think this is the right answer. And you'd find many who go, no, this is definitely not right. On the one hand, it was called the breakthrough of the year by Science Magazine in 1998. So there was some energy and momentum, so to speak, from the media. But the media is always excited about things. But from sort of hard-bitten cosmologists, I think there was a lot of but the cosmological constant. I mean, Einstein was wrong about it. It's been wrong many times. We don't even understand why there should be this much vacuum energy. So I think that the community was still uncertain. People started speculating about I will say exotic astrophysics that could explain this. So they came up with a couple of ideas, like that there was gray dust in the universe, this kind of mythical particles of stuff in between galaxies that was of the right size, grain size, so that it wouldn't give any telltale reddening or blueing of the light, which is what we looked for when we looked for the signature of dust. Or that maybe the supernovae were born fainter when the universe was younger, a process we call evolution, which we don't actually think occurs, but at the time, maybe it did occur.
Right.
And so by the late 1990s, it became clear that what we needed to do was look for even more distant supernovae, because if the universe were truly accelerating now, because dark energy was dominant, if you went far enough to the past, the universe would have been decelerating. It would have been dominated by matter.
And that's because matter and dark energy react differently to the expansion of space. So as space is expanding, all of the matter in the universe is getting more spread out. It's getting farther away. And so the density is decreasing. But dark energy, because it's something inherent to space itself, the density doesn't decrease as the expansion continues. So if you start with one patch of space and expand it twofold, the amount of dark energy increases twofold with it. So earlier in our universe's history, if you go back in time, matter was more dense, but dark energy was at the same level it is today. So at some point, the matter density would have been greater than the density of dark energy. And at that point, the universe on a whole would have been decelerating because of the attractive force of gravity between the matter. So that's the matter-dominated era we're talking about here.
And so we also have seen bound structures form like galaxies from gravitational attraction. And so if the supernovae at that point were telling us the truth, we should be able to see that phase. And so I focused on using the Hubble Space Telescope at that point to search for supernovae beyond redshift 1 and look for this turnover, which is something we saw around 2004 that showed that the supernovae were not evolving. There was not this gray dust. At the same time, observations of the cosmic microwave background were coming out, new ones,
Right.
from the ground initially in early 2000 and from WMAP in 2003, NASA's WMAP, that showed that the total matter and energy density of the universe really was 1. And so if you could just do subtraction, take 1 and subtract the 0.2 or 0.3 from the local matter density, it showed that, there was this 0.7 or so in this missing form, which matched what we were seeing. And then there were other experiments coming along. Everything began leaning to the same picture, so that by 2003, I think Science Magazine called the breakthrough of the year cosmic consensus.
So that's about what I remember too. 2003 with the WMAP results. Not every single dark energy skeptic. I knew a couple that persisted after that, but pretty much everybody was on the same page by then. And now you'd have to work pretty hard to find a cosmologist who isn't convinced by this consensus. And maybe there's one out there I can think of, but that's about
just
it.
To be clear, I mean, so this model that was born then, which we call lambda CDM, right? It's great because it fits so many different kinds of observations. That's great. But it is, phenomenological in the sense that, it tells us that 96% of the universe is in either dark energy or dark matter. And we've added those to the models because of the observed phenomenon we see. But we don't have a deep explanation for the either the nature of these things or, for example, in the case of dark matter, which is a particle, we haven't found it in the laboratory. In the case of dark energy, we really are struggling to come up with a deep explanation. And so it's a powerful model, and yet, it has elements of connect the dots. And, that's why this is still a very rich area of research.
Why This Universe is produced and edited by me, Shalma Wegsman, and our co-host is Dan Hooper. Dan is a professor of physics at the University of Wisconsin-Madison and the director of the Wisconsin Ice Cube Particle Astrophysics Center. If you like our show and you want to support us, you can join us for as little as $3 a month on Patreon. There you can also get access to exclusive Ask Us Anything segments where you can directly ask Dan and I any of your questions on physics or whatever else. And to find that, just go to patreon.com/whythisuniverse. As always, thanks for listening.